Okay, welcome back everyone. In this video, we're going to introduce the idea of a differential equation, talk about some of the basic concepts associated with differential equations, and begin to orient ourselves towards the approach we're going to take in this class towards solving them, which is a numerical approach. And I think for those of you who've had a little experience with differential equations, you'll find this different and hopefully complementary to what you already know. And if you haven't had any differential equations at all, that's not a problem because we're going to start from the basics. So let's go ahead and get started. So what is a differential equation? Well, it's just an equation that relates a function to one or more of its derivatives. Now, there's all kinds of functions out there, and so there's all kinds of differential equations. When we say an ordinary differential equation, what we're talking about is a differential equation involving a function of a single variable. And so all derivatives in the equation are with respect to that variable. And that's an ordinary differential equation. Obviously, there are functions that are functions of more than one variable, and derivatives of those kind of functions are partial derivatives. And so differential equations involving those are called partial differential equations, or PDEs. And actually, PDEs are one of the main tools of physics. A lot of the equations describing very basic physical phenomenon, like the way that waves would propagate through a medium, or the way that heat would diffuse through a solid, are partial differential equations. But in this class, we're going to be totally focused on ordinary differential equations, and that's where we'll concentrate our efforts. So here's a few examples of ordinary differential equations, kind of starting simple and getting a little bit more complex as we go along. This first one is maybe one of the very simplest differential equations, dx dt equals t. Now, I've actually got the solution there, but let's cover that up for a second because there's a pretty good amount of information you can read from the equation itself. So for instance, let's look at the left-hand side, dx dt. Right there, we've already established a couple of things. There's a function whose name is x, so x is our function here. And we're looking at its derivative with respect to t. And this is an ordinary derivative, not a partial derivative. So right now we know that x is a function of t. A lot of times I'll emphasize that by writing it this way. X is some function of t. And then what the equation is telling us is that the derivative of x with respect to t is equal to t itself. So we're asking here for a function named x, a function of t, whose derivative is t. So you can probably guess right off at the top of your head what the solution is. What's a function whose derivative is t? How about 1/2 t squared? And then you see I've added an arbitrary constant here because if 1/2 t squared solves the differential equation, and it does, right? If you take the derivative of x here, 1/2 t squared, you get t. Then I can add any constant to that function, and it would still solve the differential equation. So an equation like this, in which the only variable that appears on the right-hand side is t, is basically just an integration problem, right? If dx dt equals t, then you can just integrate both sides of that equation, and the integral of dx dt with respect to t, in other words, the integral of x prime, would be the integral of t with respect to t. The integral of x prime dt, of course, is just x, and the integral of t dt is 1/2 t squared plus c. So that's where that constant c comes from, sort of in a formulaic sense. So that's pretty easy. Take a look at the next one though, and I'll cover up the solution here for a minute as well. Very similar, except now we're saying dx dt equals x. So in other words, if we wrote this using the prime notation for derivatives, we'd be saying that x prime of t equals x. You can't solve this guy by just integrating both sides of the equation, because even if you write it out like this, if you integrate both sides of that equation, you're going to be integrating with respect to t, and you just won't get anywhere. Now, there's another way to look at it though. I'm asking in this differential equation for a function whose derivative is equal to the function itself. Do you know a function like that? Think about it for a minute, and you think about e to the t, right? And again, remember, it's implicit in the differential equation itself that x is a function of t here. So e to the t is a function whose derivative is itself. But if you think about it again, there's a constant in play here too, because if e to the t has itself as its own derivative, then so would 4 times e to the t. Think about that derivative. The derivative of 4 times e to the t is just 4 times the derivative of e to the t, which is just 4 times e to the t. So there's another constant in play here, but now it's a multiplicative constant. Instead of adding the constant here, for this particular equation, the constant comes in as a multiplier. So what explains that, and how do we deal with that sort of formulaically? Well, we're just going to kind of put that aside for the moment. There is a technique of solution called separation of variables that would allow you to solve this equation, analytically. And I'm sure if you've had a DE course, you've seen separation of variables. That's what's in play here. We're really not going to go into that in this course, though, because we don't have to. We're going to take a totally different approach to solving these equations here. So I'm not going to really talk about separation of variables much. But I do want to point out just the large difference between the solutions of these two equations, even though the two equations look superficially very similar. And so that's foreshadowing something that's definitely true of differential equations. They're nuanced. They're not as straightforward to solve as, say, like an algebraic equation or something like that. Here's a third example of a differential equation. Now, dx dt is a function of both x and t. I've got dx dt equals minus x times t. And so that's a little bit more complicated than either of the previous ones, but it's a very common situation to have in ordinary differential equations, where the derivative of the function x is expressed in terms of the function x itself and the independent variable, which in this case is t. And so that's an even more or even less obvious example. We can find the solution of this one. It's x equals a constant times e to the minus t squared over 2. So for those of you in probability, you see this as essentially the standard normal probability density function. While it may not be obvious how to solve this guy, it is pretty clear. You can verify that it's a solution pretty easily. The way you would verify that a given function solves a differential equation is just to do the computations and see if the left-hand side equals the right-hand side. So if you wanted to verify this one, we could first compute dx dt, right? So the derivative with respect to t of our function x, which is constant times e to the minus t squared over 2. So the derivative of that would be constant e to the minus t squared over 2. And then by the chain rule, I need to multiply by the derivative of the minus t squared over 2. So that's minus t. And you, of course, recognize that as this piece right here, c e to the minus t squared over 2, that is our x. And so we have x times negative t here. And of course, what we just computed, the d dt of x. So we do see that this function satisfies the differential equation. Its derivative, dx dt, is equal to just x times negative t. Again, you can get that solution as well by the method of separation of variables, but there are plenty of differential equations that can't be solved by that method. In fact, we'll see one pretty shortly here. There's a related concept that I wanted to bring up at this point, and that's the idea of an initial value problem. So you notice that all those d's on the previous slide had a constant associated with them. The solution of just the differential equation itself had an arbitrary constant, and that essentially comes from the idea that when you integrate a function, you get a constant of integration. An initial value problem has an extra specification that often allows us to solve for that constant. So here's an example of initial value problem. I've got the same ODE as we had before, so that's my ODE right there. But then I include a condition on the function. I ask that, in this case, the function, when evaluated at time t equals 0, be equal to 5. So when the input is t equals 0, the output of our solution should be 5. This is called the initial condition for the problem. And those two things together, the ODE along with an initial condition, are called an initial value problem. If you have the solution for the ODE, the solution for the initial value problem is usually pretty readily available. We saw on the last slide that the solution to our ODE was constant times e to the minus t squared over 2. To work the initial condition in, just remember that when t equals 0, x is supposed to be 5. So if I plug in t equals 0 to this and set it equal to 5, you get c times e to the minus 0 squared over 2 equals 5. And that enables me to solve for c. I see that c has to be 5 in order to satisfy the initial condition. And so the solution to the initial value problem is x equals 5 times e to the minus t squared over 2. So initial value problems typically don't have that constant of integration associated with them because you use that constant to satisfy the initial conditions. Now, one thing that you may not get in a first course on ODEs is this situation that I want to talk about here. The solution to an ordinary differential equation are often what we call non-elementary functions. That means, in contrast to the examples I've just showed you, many, if not most, ODEs have solutions that are not expressible as finite combinations of functions we're used to dealing with in courses like calculus. That is, they're not expressible as finite combinations of rational functions, and that would include polynomials, right? Trig functions, exponential functions, and their inverses. And so a function like that is called non-elementary, and it's just a fact of life, or a fact of mathematics, that many simple ODEs have solutions that are not elementary in that sense. You can't really write them down in a finite way in terms of ordinary functions. Here's an example. This is a pretty simple ODE to just write down dx dt is x squared plus t, but you can prove that the solution of this differential equation, and it does have a solution, but you can prove that it's not expressible as an elementary function in the sense we've just defined. It turns out this guy has a solution that you can write down in terms of Bessel functions, if you've ever heard of those, but Bessel functions themselves are not elementary. They're not, finite combinations of rational functions, trig functions, exponential functions, and their inverses. And so this points out a basic need in ordinary differential equations, which is a need for numerical solutions and approximations. And so that's kind of the approach that we're going to be taking in this class. And so that really is almost it for this first little lecture. I wanted to, one other thing I wanted to sort of get out there in this lecture, and it's really simple, but I wanted to sort of standardize the kind of problem that we're going to be looking at. So in general, we're going to be looking at a first order initial value problem, which will take this form. So the derivative of our function x that we're trying to find here is going to be expressed as some function of both t and x. So we've already seen examples of that. And we're going to have an initial condition as well. X at some initial time t0 is equal to some value x of 0. So that's the kind of problem we're going to be looking at. We're going to consider two basic solution techniques. The first is solution by power series. And this will bring into play some ideas we've already been using heavily in the course, including Taylor's theorem and in particular Taylor's theorem. And then we'll also look at an idea of iterative solutions of initial value problems using numerical techniques. Before I take leave of you this time, let me just talk about what I want to call the standard form of a general initial value problem. And this is kind of a prelude to this power series idea. Basically, the idea that we're going to first look at is, given an initial value problem like this, let's expand the solution in a Taylor series centered at the initial time that is specified in the initial condition. So in this case, we would try to expand the solution in a Taylor series centered at t0. Well, I would really like not to have to worry about different values of t0 here. I would like to always have my initial condition starting at the same place. And so that's what I'm going to call the standard form of an initial value problem. So the standard form of initial value problem is really just pretty much an initial value problem, except we require that the initial time be t equals 0. So that's the only difference. And there's a kind of a quick and easy way that any first order initial value problem can be put in standard form. And so let me walk through an example of that real quick here. Here I've given you an example of a first order initial value problem. Dx dt equals 2 times x plus 3 times t with an initial condition that x, when t equals 4, x should be 5, right? X of 4 equals 5. So that's our initial value problem. Now, to transform this, what we want to do is write down an equivalent problem in which the initial condition is at time t equals 0 instead of time t equals 4. To think about that, let me write the problem down in a slightly different way. I'm just using prime notation here. So the initial value problem could be written as x prime of t equals 2 times x of t plus 3 times t. and x of 4 equal 5. Now, to change it to standard form, what we want to do is essentially make a little substitution. Let's consider a new function y of t that's equal to x at time t plus 4. So the idea here is that when t is 0, y of 0, in other words, equals x of 4. So if I could, which is 5. So if I could write an initial value problem down for y, that would essentially be equivalent to the original initial value problem we have up there. After all, in terms of just the functions, y is simply the function x shifted 4 units to the left, right? That's all we've done really there. But what initial value problem would that correspond to? Well, you can just work it out by using a little calculus here. So look at y prime. If y of t was x of t plus 4, then y prime of t is x prime of t plus 4 times 1 by the chain rule, but that doesn't change anything. And then go back and use the initial value problem for x. What would x prime at t plus 4 be? Well, x prime at any time is 2 times x at that same time plus 3 times that time. So x prime at t plus 4 would be 2 times x at t plus 4 plus 3 times t plus 4. So the idea is we're relating these two and just plugging in t plus 4 for t. But of course, x of t plus 4 is y of t. And then 3 times t plus 4, I've just expanded that to be 3t plus 12. So what we have here is that y prime of t is 2y of t plus 3t plus 12. And so rewriting that using the Leibniz notation, we get dy dt is 2y plus 3t plus 12. And of course, we already saw that y of 0 equals 5. And that is an initial value problem in standard form. So we'll do a little bit more of that as we go forward. But basically, as we start, what we're going to do is consider initial value problems in standard form. So that means that we'll be looking at initial conditions that are always at time t equals 0, and when we do our Taylor series expansions, they will always be centered at 0, which is a little simpler than having them centered somewhere else. So anyway, there will be a little homework assignment that just has a couple of problems to verify a solution of a DE and to put another initial value problem into standard form. So hopefully this lecture will have helped you with that, and I will see you soon with a little bit more about ordinary differential equations. Y'all take care.